Okay, two phenomena. The photoelectric effect, right? According to Einstein, a photon of energy of a certain threshold frequency comes down and moves an electron away from its nucleus. I mean, that's what's happening here. This is why the electron was being held by the nucleus of the atom, right? The attraction between the protons and electrons. And if you come in with enough energy, that electron gets moved away from the nucleus. At the same time, if you take white light and you run it through a prism, all right, you break that light up into its components, we get a rainbow, right? We get a continuous spectrum of all the different frequencies of light that make up that white light. So this is what a rainbow is, right? When the sun comes through the water, right, the light waves get bent and we see the different frequencies that make up that white light. Now, when we take energy and we put it into something like hydrogen gas and we bend that light, right, all of a sudden it's a black body, right? You put energy into it, all of a sudden the hydrogen gas starts to glow. When we bend that light, we don't get a continuous spectrum. We get a broken spectrum. So only certain frequencies make up that light rather than a continuous frequency. We only get a red line, a green line, a blue line, and a purple line with hydrogen. With neon, if you did the same thing, you get a more complex spectrum being given off, right? Set of frequencies, but nonetheless broken, right? Only certain frequencies are allowed. So the question is why? Why only certain frequencies allowed when you put energy into a black body like hydrogen gas and it starts emitting radiation? So this was the question of the time. And the one who comes along to explain that is Niels Bohr. And what he does is he turns Einstein's photoelectric effect around. Instead of looking at energy going in to move electrons away from the nucleus, he explains that spectrum as electrons coming down from what he called an excited state, right? Electrons away from the nucleus, giving off the energy that you put into it, and only allowed to come back to certain positions. So what he does with this is he quantizes. He makes it so that the electron around the hydrogen atom can only be at certain distances. That's why only certain frequencies come off. So this is what you get, right, with excited electrons, we'll call it excited electrons. You put energy into electrons, you move them off, right, according to the photoelectric effect. Now when they come back towards the nucleus because they're being attracted, they give off that energy you put in, and they only come back to certain distances. So this is what it looks like, right? You zap that electron with energy, you move it away from the nucleus. Now it wants to come back. It's at a high potential energy here, right? It's being attracted by the nucleus. When that electron comes back to the second energy level, the second energy position, that's when you give off a frequency of light in the visible range. So coming back from the fourth energy level to the second, you give off a green photon. Coming back from the third energy level to the second energy level, you give off a red photon. And coming back from the fifth energy level to the second energy level, this is where you get your blue photon, and so on. You might be saying to yourself, well, why don't you go back to the one? Well, the electron does go back to the one. It's just that if I was to do this more to scale, right, if this is the first energy level, the second energy level would be somewhere here. And then you get shorter jumps, third energy level here, fourth, fifth, sixth. When the electron comes from, say, the second energy level out here back to the first, that's a big jump. So you're getting a photon that's outside of our visible range. You're getting it in the ultraviolet range. And when you have a jump back from the when you have a jump back to the third energy level, right, when an electron comes back from the 4 to the 3, that's when you get it in the infrared, right? It's too long a wavelength for us to see. So the bigger the jump, the higher energy photon that comes off, right? We get the red jump, the green jump, now we get the blue jump, right? Higher and higher frequencies, the bigger the jump. The jump back is where you emit energy. So Bohr, being a classical physicist, still saw the electron moving in a circular orbit, and he had this beautiful math to explain why the electron was traveling around the nucleus like the moon around the Earth, but it's totally wrong. That's not how the electron stays. This is not how the electron stays outside of the nucleus. What he's right about, totally right about, is that only certain distances from the nucleus are allowed. So you've quantized certain orbits. Now, when the electron gets excited and it moves away and comes back to that lower state, this is where certain frequencies of electrons are being given off. So the excited state for an electron is anywhere other than the lowest energy, which is called the ground state. So when the electron is sitting down here in the first energy level, that's the lowest energy state. When you hit it with energy and it moves out, it's at some sort of excited state. And when it comes back down, that's when it gives off a frequency of energy, either in the visible range or outside. So this is how you explain the spectrum for the different atoms. Those lines, these lines right here, are like a fingerprint for this atom. Only hydrogen has this spectrum. Neon is the only, where is it? I lost it. Huh. Where did it go? Oh, there it is. It's below the question mark. Neon's the only one with this spectrum, right? So these are like fingerprints for the different gases, right? When you excite the electrons and they come back down to their energy levels, this is the pattern that's given off for neon. This is the pattern that's given off for hydrogen. So, is energy emitted or absorbed in the following electron transitions? So when you're coming from a higher energy state, the fourth energy level, back to the second energy level, this is where you would be emitting energy, all right, in the green spectrum. When the electron goes from a radius of 2.12 angstroms to one of 8.46 angstroms, what this implies is that you're moving the electron out, right? So this is the photoelectric effect. You zap the electron with a certain photon of energy, with enough energy to move it out to that certain energy level, and that would be an absorbing process. And when you take an electron away from hydrogen, you get an H plus ion. That hydrogen ion wants what? It wants its electron back. So if you introduce the electron to an H plus ion, that electron coming back to any energy level would be an emitting process. So we still haven't answered the question, why? Why would the electron stay outside the nucleus? Okay, so it's quantized. It's only at certain positions. That makes sense, right? That explains the emission spectrum for the different gases. But why? Why does the electron stay out? To understand this, we go to de Broglie, who goes back to wave-particle duality. When we have something really small, like an electron, if you look at wave-particle duality, right? If you have mass, you have a wavelength. So if you have a big mass, like in the land of the big, I mean, you have mass. Do I have a wavelength? Technically, yes, you do have a wavelength. But you are so massive that your wavelength is so small, it's inconsequential, it's meaningless. But in the land of the small, when you get very, very small masses, all of a sudden, that particle starts having a significant wavelength. So all of a sudden, the electron is not acting like a particle anymore, it's acting like a wave. So it's like a standing wave. It's like a guitar string being plucked, right? It stands at a certain position. So when it's acting like a standing wave, only certain wavelengths are allowed. You're allowed this wavelength, as long as they constructively interfere, the wave can stand at this position. You try to put a fractional value in there, you get destructive interference and the wave disappears. This is why electrons are allowed to stand here. You get constructive interference. And allowed to stand here, you get constructive interference. But anywhere in between, you get destructive interference and no wave. So the electron's acting like a wave here, the electron's acting like a wave here, there is no wave here. So now all of a sudden you can explain why the electron only exists at certain positions. It's not acting like a spinning particle, it's acting like a standing wave. Along with this, we have what's called the Heisenberg uncertainty principle, which means in the very act of trying to find the electron by shining high frequency light on it, you move it. So you can't actually know where the electron is, right? This is his equation. As you start getting very accurate in terms of position, you get very inaccurate in terms of how fast it's moving. So, and vice versa. So you can never know these two things at the same time, having a small value, right? They got to be equal to this constant. So as this gets small, this gets big. As this gets small, this gets big. So you can't know the two things the same at the same time. So just by its very nature, you can't actually know where an electron is. Einstein hated this. He spent most of his career trying to disprove the uncertainty principle, and latter career, I should say. And the more he tried to disprove it, the more he proved it. So this is the nature of an electron. You can't actually know where it is, and it's behaving like a standing wave. So, in many cases, the uncertainty about the whereabouts of an electron is greater than the size of the atom itself. So it goes on forever in terms of where the electron can be. All right, so the last person on our list puts all of this together into what's called quantum mechanics, a set of equations that gives you a distribution of where an electron's likely to be. So the way that you view this is you have a high density close to the nucleus and you get fuzzed out density of this probability distribution as you get away. So this is what you get as to where an electron position is. High probability close to the nucleus, low probability away from the nucleus. So sometimes this is called the cloud model, right? The electrons exist in these clouds. Well, really what those clouds are probability distributions. So the square of the wave equation gives us the probability density map of where an electron statistically is likely to be at any given instance in time. So when you solve for the Schrodinger equation, you get three-dimensional space as to where an electron is. And it's hard math. This is crazy math, right? I mean, you get to third year chemistry, you deal with this equation and just trying to solve for it using some, calculus. And guys, these are solutions to the Schrodinger equation. You get an infinite number of solutions to the Schrodinger equation. So this is the first solution of the Schrodinger equation, and it's this space where an electron is likely to be is defined by three numbers: an n number, an L number, and an ml number. So 1, 0, 0 corresponds to this density probability plot. 2, 0, 0 corresponds to this density plot. Now, you don't have to know these equations. What you do have to know is that these three quantum numbers that get spit out of the Schrodinger equation are like addresses as to where an electron's likely to be. So an electron can be at this address, 100, or at this address, 200, or at this address, 210, or 211, or 21-1, and so on. So what I want you guys to know is what these addresses stand for, right? These are probability distributions of where an electron's likely to be. And they're defined by a set of three quantum numbers. So instead of talking about orbits, we talk about orbitals. Orbitals are probability distributions of where you're likely to find an electron. So write that down. Orbitals. These are where the electrons are. Each is described by a set of three quantum numbers. So there's an n number, which represents the distance from the nucleus. There's an L quantum number, which indicates the shape of the distribution. And then there's an ML quantum number, which corresponds to the orientation of that shape. And we'll get into that in the next video. So, distance from the nucleus versus probability distribution. High probability being close, low probability being far away.